Yeah, our next speaker is Professor Arun Tangirala from IIT Madras and IIT Tirupati. He is going to talk about data-driven methods and a few applications he had been involved in. Thank you, Arun, for coming from Tirupati.
Oh, thank you very much. So I bring you the blessings of the Lord. Thank you very much. Very good morning. It's great to be back within 2 weeks. There are a lot of questions on causality analysis. So if you're interested, 2 weeks ago, my talk was entirely on causal climate networks. So I think the video should be available in the workshop. Please refer to it. Of course, I'll briefly go over that in today's talk. It's a loaded presentation. I hope that I meet the requirements of the clock. Okay, so I'll talk about data-driven methods in C for climate, W for weather. And I'm not going to really talk about the very traditional ML or AI approaches. I think you've been really given a very good introduction to that in the previous talk and perhaps in some of the previous talks in the days earlier. I'm going to actually float some ideas that we have been using, what we call as recipe learning from domains. Now, see, if computer science folks have the freedom to float 50 different kinds of learning, everybody on this earth has. So I call this as recipe learning. So if you want to coin that and do think about me, you don't have to quote me on this. But what essentially the idea is, I'll give you an anecdote. This goes back to Chanakya time. I'm sure everybody has heard about Chanakya. And he was really keen on making sure that Chandragupta Maurya is the king, and he was really struggling to do this. But he was a very talented person, as all of you know. But there's one mistake that he makes in the course of time in attacking Magadha, in really uprooting the current king, which is that he straight away attacks the capital city, and then he gets defeated. Well, he doesn't attack, but he basically asks Chandragupta Maurya to attack. So they lose the battle, and then he takes shelter in a hut. And I mean, this is, I don't know, it's all anecdote, but makes sense. And then he takes shelter at the hut of an old lady, and she has a grandchild. She cooks the food, and it's the eating time. And the child is actually trying to eat from the core. It's very hot. So actually, he's really putting his hand into the core. And the mother, if I'm right, says, don't really put your hand in the core. Try to eat from the peripherals because they will be cooler. Okay? So that learning, Chanakya is observing this conversation. And this is an eating domain, okay, which we go through daily. Chanakya realizes that's exactly the mistake that he made. He shouldn't have really attacked the core capital city. He should have started conquering from the borders, right? And then he takes this learning and goes.
Yes, this same story, I just heard the same story, not regarding Chanakya and Chandragupta Maurya, but regarding Shivaji.
Yes, so you can replace X with Y and Z with W. Please go ahead. But the entire story makes sense. And the purpose of quoting this is to tell you how we can learn from different domains very easily. And a lot of the algorithms that you see today in optimization, ML, AI, and so on are all, many of them are inspired from other domains. For example, the swarm optimization algorithms, the simulated annealing, and so on. They're all inspired by other domains. And this is what exactly I'm going to talk about. So I'll take you through the problem formulations. That is, when we were presented with forecasting problems, anomaly detection problems, and so on, I predominantly work at the intersection of two fields, which is the process systems engineering and data science. Okay. So today, this is called process systems intelligence and so on. So when we were presented with these problems, we asked, should we go with a run-of-the-mill, marry the data with the Python, Nagaraj routine or whatever, and dump everything into one model and keep going? Obviously, it won't work. Or should we really take a couple of steps back and ask, how do we formulate this problem for the given application, right? And that's the kind of experiences that we want to share, that I want to share, and talk about how certain parallels now are evolving in the climate and weather. Well, of course, I'll also share some of our results in climate analysis as well. And in that process, we'll go through causal discovery as well. Okay, so the broad framework for our research is essentially based on 4 pillars. The systems theory, you can say linear and nonlinear dynamical systems theory. And then, of course, the, as I say, the Mata and Pita, I and ML. I in Marathi is Mata and data is Data, father. So today's Mata and Pita is I and Data, AI and ML. And then, of course, you cannot ignore, as all of us understand, the whole uncertainty modeling that prevails, whether it is data or real life. We should learn to embrace uncertainties. And we were having an exciting discussion yesterday after dinner. And then the modern network paradigm. So our research really is based on these 4 pillars. And of course, we cannot ignore the domain knowledge. As and when needed, we'll have to customize it. So we call this as Siddhanta. Yeah, I mean, of course, you have to be inspired by bureaucrats who come up with fantastic acronyms. Why not academicians? So Siddhanta stands for quite a bit: systemic, intelligent, data-driven, and network theoretic analysis. But please remember Siddhanta. That's good. It has its own meaning. And we use this for various applications across domains. So the different domains that we have traversed are all the way from under the earth, seismic, into the space, and of course, atmosphere along the way. And on the earth as well, transportation. So these are the broad classes of problems that you run into. Learning is a modern word. And a lot of people really they have tough time learning what is learning because it's so confusing. Learning could mean, broadly, it is decision making, but it is also used for modeling. And again, within modeling, people argue that estimating parameters is also decision making. Anyway, so we call that as learning, and then you have forecasting, one of the most interesting problems, even to a layman. And then monitoring. By monitoring, we mean abnormal situation management, or there are different names to this, alarm detection, and so on. Then analytics, of course, all of us understand that. Then there is sensing, which I'll not talk about today. We use a lot of ML models to build what are known as soft sensors, where hardware sensors are not available. Okay. So I just wanted to talk about a couple of things in terms of advances in data science and advances in models, right? So in terms of advances in data science, everybody is familiar with AI and ML, but what role does it play? A lot of us are not so sure. Now, of course, AI and ML itself draws ideas from different fields and then again feeds back. So with the arrival of artificial intelligence and ML, you can now think of new age sensing. Okay, so you can think of many ways of sensing things that you could not think. And it has to incorporate uncertainty analysis. This is a bit weak right now in AI. A lot of models assume deterministic processes and so on. Yes, there is a niche sector that focuses, incorporates uncertainties. NLP, as we all know, even Bacha knows today about ChatGPT. So the natural language processing technology has taken the world by storm and continues to create storms. There is this cyclone Fengal coming up, but that is nothing as compared to what storms we are seeing in ChatGPT, in the NLP technology, in the LLM world. And then, of course, phenomenal computing advances, including quantum computing and so on. So they're all really propelling things like crazy, that if you are Kumbhakarna, that's it, you will lose everything. I mean, you will be out of place. Even if you sleep for 2 weeks in academia world, you have lost. You have to really work hard to know what's happening in the world. Okay, so you can't really take a break types. And what can AI and ML do for you? It can really now allow you to handle problems and come up with innovative methods at large scale. And it can facilitate higher level and remote automation. Many plants today, industry plants, are now relying on this too. In fact, in education, this is true. Online learning, we are doing this, right? Not just engineering. And now we can think of operating highly complex processes in an efficient way. And of course, the one that's very relevant to the climate world is leading to the development of advanced simulators and forecasters, the ClimSim and all of that coming up, and neural GCM and so on. So there are a lot of things that are happening in a big way. Okay, so that's about advances in data science. Now, when you turn to models, the traditional backbone of modeling has been systems theory. So where you think of the process being driven by certain inputs, and then of course this outputs means measured variables, and then there is uncontrolled factors called disturbances. Of course, if you have autonomous systems, then you don't have inputs and so on. But that has been really the backbone of modeling for a very, very long time, and it will continue to be. It has a fantastic formalism attached to it and so on. But over the centuries, network models have really started to show their might, and especially in the last couple of decades. What is the advantage of working with a network model vis-a-vis a standard, let's say, set of ODEs or PDEs and so on? One of the biggest advantages of working with network models is they can give you the skeletal structure of a process, which is sufficient in many applications. See, ODE models, PDE models are very detailed. If you have to build such models from data, you need very rich data, lot of data and so on. But in many applications, I'm not interested in such detailed interactions between variables. I just want to know how they are connected. That is sufficient for disturbance propagation, root cause analysis, etc. So from a data standpoint, it's much less demanding on the data. So networks allow me to build in a hierarchical manner. I can start with the most basic skeletal structure, even without the directionality. So here you see arrows on the edges showing the directionality of the effect, right? But I don't even need that in a few, in several applications. And those networks are called correlation networks and so on, where the directionality is not of interest. But the moment directionality is of interest, then it becomes a causal network and so on, right? And you can progressively build. I'll show you one schematic later, which shows the progression from correlation networks to directed networks, weighted directed networks, and so on. So the main point is I can hierarchically encode information at different layers, and the data requirements will progressively increase, which is not the case with ODE models. You require large amounts of data and so on, and that may not be needed. And the other thing, of course, is that you don't need to really classify something as an input and output and so on. It's all built in. Depending on the directionality, you can think of what is the driver, what is the effect, and there are variables that act as both, right? Why should a variable act as only a source or an effect? So it can comprehensively model many processes. And the third biggest advantage of networks is the mining of the network that you can do. That is, you can exploit the network properties starting all the way from degree of a network to adjacency. Adjacency matrix is the full information about the matrix, but you have several network properties which are also called network measurements. Just like a tailor takes measurements of a human being, you also take measurements of a network and call it as network properties. Obviously, all of this is inspired from graph theory. Okay. The formal graph theory goes back to 18th century. Euler is considered the father of graph theory and so on, the famous Königsberg bridge problem and so on. You can look up. And when you look up that, you will read that Euler could not have solved the problem without the graph, at least graph theory, because the prevailing math and even today's math was very difficult to solve the problem that was given to him. So he had to really come up with a new mathematical object called a graph. And since then it has inspired, it has troubled you in chemistry courses and so on, all the molecular structures that you see and so on. Yeah, all that karma goes to Euler. That's it. Just as the way many karma goes to Fourier, Euler is also. So the good and bad karma, all the cursing that you do before the exams and so on. Anyway, so there are several advantages of working with networks, and they're very attractive. And they're just growing. The adoption of network models is just growing, but you have to be cautious. You should know what type of network is being talked about, because there are different types of networks that you can think of. See, today banks in India especially, they say you have to fill KYC even if you're no more. Okay, so every 2 years. So KYC is know your customer, yeah, right? You have to also know your network, KYN, which network you're dealing with, what is the network that the paper is talking about, what is sitting at the node, what is the, encoded in the edge, and what are rules for drawing the edge, and so on. Now, at least there are 3 broad classes. One is called the complex networks, which has really picked up momentum in the last decade, where the nodes contain the time series, entire time series sits at a node or a state, and the edges denote obviously some kind of association, directed or undirected association. Then you have networked systems where systems are sitting at the nodes and the edges are saying how the systems, subsystems are interacting, how the liver and the heart are interacting, for example, how a reactor and a heat exchanger are interacting in a plant and so on. Then you have multi-layer networks where the network itself is a node. Okay, so there is a layer. A very classic example is the interaction between a climate network and an infrastructure network, or a healthcare network, or a transportation network. The moment there are changes in the climate network, the transportation network or the infrastructure network is also disrupted, right? So these are also becoming very popular. And you can choose to spend your entire lifetime or your next 10 births or whatever in one area, and still there'll be enough to do. Right? Good. So this is good news for all researchers. Don't get depressed, because PhD beginners get depressed. Oh, everything is done. There's nothing for me. Okay. So just a quick glimpse into traditional time series modeling, because Vishal told me, please also consider that there are beginners in this audience who are trying to get into the data science wagon. So traditionally, the way time series models are built, and this workflow applies even today. Doesn't matter what you do, whether even if you're building the deepest neural networks, same approach. So you acquire data, you have to inspect data, you have to do the so-called data laundry, visualize, don't undermine visualization, see what you are plotting, and remove trends, or you account for non-stationarities. A lot of methods assume that your data doesn't have trends, and your data is so-called stationary, which means its statistical properties do not change with time, and so on. That is in the stochastic world. In the deterministic world, stationarity means the frequency content does not change with time, in the linear deterministic world. Once you have done all this pre-processing, which unfortunately takes about 70% of your overall time, okay, but that is very essential. Then you actually get into modeling or filtering and so on. But you have to keep the end use in mind. So also, although the workflow is in this direction, you have to think backward. So you have to ask, what am I doing my data analysis for? Is it publishing a paper? That's not included here. But we want to look at some serious one. Is it forecasting? Do I want to detect periodicities? Do I want to just do spectral analysis, classification, or anything else, right? Anomaly detection and so on. Start from the end use. It's like just, buying your furniture, buying your car. If you say, no, I have a lot of money, I want to buy furniture, then you don't need this workflow. But you start with the need and then determine what you want to do. Regardless of the end use, these steps are inevitable. Now, typically, so there is a lot of rush to build models today. So when data is given, bring Python and bring a computer and scikit and so on, and marry, and that's it. So you are playing the role of a priest or a father. That's it. Okay, and then you say, take it. Don't ask me what it did. Okay, that is 90% of data science today. You don't want to be in that league. You really want to question every assumption that is made and subject the data to as many tests as possible so that you know what you're doing. Okay? If you don't care what you're doing, then you're in a different league. All right. So stationarity, for example, there exists many stationarity tests. I mentioned earlier what is stationarity. Then there is something called heteroscedasticity, where the variability in the data is changing with time. Strictly speaking, the variability in your prediction errors are going to change with time. That means your prediction reliability is going to change with time. So what will you do upfront to capture that? In fact, this was a big problem in the 80s, and finally it was solved, at least partially, using what are known as Arch and Garch models today by an econometrist who went on to receive a Nobel Prize in economics and so on. It turns out that And this is where slowly we start understanding the domain connections. It started in econometrics and people started realizing heteroscedasticity exists in hydrology, exists in seismic signals, and so on. So you see heteroscedasticity in many, many domains. And that is what gives you the universality of certain characteristics and principles. So there are many tests for heteroscedasticity. Then when you're building linear models like ARMA models, ARIMA models, SARIMA models, VARMA, KARMA, all these models that are existing, KARMA is the supreme. All these models are based on the assumption of linearity. There are tests for linearity. Please make sure that you subscribe to that, okay? And you are aware of it. And then a lot of models, especially the linear models, in fact, linearity and Gaussianity are equivalent to a large extent in the stochastic world. Make sure that you're doing tests for Gaussianity. And here is where 99.99% of the people make mistakes. They get the data, they plot the histogram. If it looks like a Gaussian, the process is a Gaussian. That's the most horrible mistake you can make. It is only true if the data is so-called IID. If there is any correlation structure in the data, your histogram is good for printing and putting it up on your wall, but it has nothing to tell you about the Gaussianity of the underlying process. Okay? So there is a systematic way of determining the Gaussianity of the process. So please be aware of that. Of course, I need an entire semester to talk about each of all of this together, and I do that in my MOOC on time series analysis. Please do see the NPTEL course. Okay, so once you have done all of this, then you'll have to go through the standard model steps. You'll have to choose your model, do a model validation, and then be able to explain why this model works and so on, all backed up by statistics. And time series modeling, one of the analogies that I like to give is, you're given sugarcane. A lot of you must be familiar with sugarcane. I don't know. You're familiar with sugarcane. Have you seen sugarcane in India? It's basically a stick, it's a plant with a lot of sugar in it, right? And sugarcane juice is very popular in India. Yeah, please do that. Usually it's more popular in summer because it cools your body. So there is pulp which holds the sugar, the juice inside it. So if you see how a sugarcane operator works, it takes this sugarcane from a crop. So you think of the crop as a random process. You think of the sugarcane as a single realization, that is your data set. And what you are interested in, the predictable portion of the data, right? The juice is a predictable portion. The pulp is the one that is not useful to us, but it is the pulp that is holding the juice together, not the other way around. So every stochastic signal has an uncertain, irreducible uncertain component that is holding the predictable portion. So it's all about separating. So you can learn, again, this is recipe, domain learning. You don't just drink sugarcane and come, think, can I use this idea? What does a sugarcane operator do? Any of you, do you know? What does he or she do? You have drank sugarcane juice. So what is your observation? That's it, one round? No. So what is he doing in each round? Testing for any leftover juice. That is exactly the approach in time series modeling. You build a model, look at the residual. If it is still has a predictable portion, statistically, then you put it. So obviously, you don't expect the operator to do a statistic test there. He's just touching and feeling. That's it. He knows. So overfitting is essentially the pulp going into the juice. Underfitting is the juice going away with the pulp. And just as the way the operator is actually separating the juice from the pulp, there is a thin line, right? Experience will train him. You also as a data scientist will know where to draw the line between overfitting and underfitting. And that's very important, okay? So you see, every domain is equally knowledgeable. It's just that you have to think about it. Okay. So when you apply the standard approaches, yeah, they're very good. Systematic procedures are good, but it is important to contextualize it. And that's what I'm going to talk about in the next 3 or 4 applications. What one has to respect are the process characteristics. That is the process multi-scale? Climate, of course, climatic processes, biological processes, and many even engineering systems are multi-scale. Non-linear, time-varying, deterministic. You have to ask these questions, don't rush. Then, what is the nature of your data? Is it a textual data? Is it an image data? Yeah, today you hear multimodal data and so on. Fine, but we are still not into there fully. You still have powerful algorithms meant for only numerical data, meant only for image data, and so on. And more importantly, you need to know the spatial temporal resolution. So I'll show you one application in crop yield prediction, where we have to take into account data coming from different sources: satellite data, crop yield data, weather data, soil moisture data. They're all available at different resolutions in different forms. How do you fuse all of them? Right? So, like a very good chef, you should know when to use what type of data. You cannot add all the ingredients at once and say, here you go, I'll put everything in the pan and whatever comes out is what you eat. No, that's not how it works. You have to add the chili powder at the right time, right? You have to add the salt at the right time. So that's exactly what we did in our crop yield prediction. So that's a recipe that you have to come up with. And then you'll have to worry about measurement errors. If you don't respect uncertainty, then uncertainty will actually take you for a big ride. So one has to worry about missing data, outliers, and so on. And finally, some practicalities: computational power, model maintenance, end use, and so on. So the question is, if we can use the recipes or templates developed for one domain, can it be transferred to another domain? So today you hear about transfer learning quite often in the deep learning community, right? I'll talk about that. Anyway, so the first application I want to show you is detection of P wave arrivals in seismograms. So what is a P wave? When an earthquake occurs, it is sending out some strong waves, and they are of different types. The first wave to come is the P wave. They say that nature is like mother. When mothers get angry, the first look is not the deadly one. The ones that come later are the ones that are deadly. Okay, so we have all experienced that. So the P wave travels with the maximum velocity, giving you the message that an earthquake is, the more damaging ones are coming. When? In a minute. Okay, max about 2 minutes time. That's rare, depending on where your station is. So if you can detect the arrival of P wave, we would have done a lot of favor to ourselves by shutting down critical installations, etc., saving property and, of course, lives. So what happens is, when you have low quality seismograms, so when there's no earthquake and you look at the measurement at a seismic in a seismometer, from a seismometer, you will see what is known as seismic noise. That means there is some murmur all the time because of Earth's own activity. But when a P wave arrives, of course, the signal characteristics will change. But whether you can hear this in the this whisper in the noise is the challenge. And if the so-called signal to noise ratio is very poor, then it becomes very tough. Okay. So the challenge for us was that from low quality seismograms, how do we detect the P wave, and also that the lead time is very low. So we turned to process systems engineering and asked, have I seen this problem before? Okay, so that's the beauty of working in process systems engineering, that it puts you at the interface of so many fields. You can because systems engineering is domain agnostic. The principles are universal, more or less. So if you have worked in so-called process analytics, data analytics, which preceded data science, then there is a word called statistical process monitoring, where you actually take measurements and use multivariate statistical tools like PCA and so on. You separate the deterministic component from the stochastic component, and you use what is known as a predictive approach. You predict what's going to happen, and if there is a difference between what you observe and predict, and you have to obviously build a statistical threshold for it, then you flag an alarm. Okay, so this is the idea. And over the years, just about when I was doing my PhD, this so-called multi-scale approaches developed, really took a lot of prominence, where you decompose or you project the data onto different time scales. Why should we do that? Because you have measurements, sensor dynamics at different scale, time scale. Then you have, within the chemical plant, each unit actually having different time scales and so on. So it may be a good idea to really decompose into multiple scales, and then you apply these methods. So we did that. So we said, we'll first develop a time series model for prediction. And then we use what is known as a wavelet packet transformation, which essentially decomposes the signal into packets which are characterized by certain time intervals and frequency band. When you get the data, your signal can contain frequencies anywhere between 0 and Nyquist frequency, which is half the sampling frequency, right? But that's too large a scale. You want to zoom in. Why do we want to do this in this application? Because the P wave is typically between 2 and 5 hertz. We don't know exactly what it is, but by and large, it is between that. Whereas the seismic noise is in a different band. In the time signal, it is very hard to resolve it. But the moment you zoom into frequency, it becomes very easy. So you go to a different domain, just like you can separate the dirt from the cloth only in the water domain. You can actually separate, again, that's a learning that you get from laundry. So don't think that just because you took a formal course in Fourier transforms, the guy who's washing the clothes has less knowledge. Okay. So we zoom into that frequency band and also in a sliding window. And this is done formally using wavelet packets. And we select the packet that has the signature and apply a statistic. That's the whole idea. Okay. So I'm going to skip this slide. I've explained to you what it does. And here are some results. Of course, these results are available in the form of publications. Please refer to them. But this is a result from one of the stations in Mexico. And I'm just showing you this x-axis is the window, the time window. And I'm just showing you where an event has occurred, when a P wave, when an earthquake has occurred, and how the statistic detects it very well. That means it exceeds this threshold, zoomed in here, in 2 different packets. So there are many packets, okay, that the data gets decomposed into. And just for you to compare with some of the existing methods, by the way, the literature on this is very rich, 40 years. So that again goes to tell you, just because there is humongous literature, it doesn't mean that that you cannot contribute. You need to be really asking the critical questions and ask, how did people approach? And what will be my approach? So there is always room for contribution. And you can see the proposed method outperforms many of the existing methods, especially when there is low quality seismograms. So high quality seismograms, you'll get similar performances, okay? Okay, so what about this idea in climate modeling? So I did a search. Are people using wavelets? Of course. In fact, this is one of the earliest guides that really threw light on how to apply wavelets in almost all engineering applications. In fact, many software packages were built on this practical guide by Torrance and Compo. And that's when I started reading, I was introduced to ENSO, sea surface temperature, all the climate terminology that you come into. And we used a lot of these ideas extensively, especially the tools, the practical implementations and so on. So the birthplace of practical implementation of wavelets is in climate, right? Interesting. Then that must be an old one, you say. No, there are many new ones that you can see. And people are using wavelets or multi-scale approach. You don't have to, again, get possessive about wavelets. But the whole idea is we want to use multi-scale approach in understanding, modeling, analyzing climate processes. And that, my firm belief, it will enhance the forecasting or even predicting the extreme events and so on. The skill of predicting those events better than your standard single scale approaches. So even if you're using a deep net model planning to use, make sure that you decompose. And again, there is an art there. There is a science, there is an art. So you should know how many scales to decompose, whether they make sense. Are you able to explain why this many scales and so on? Again, don't get into the Python routine mode. Okay. So don't keep, yes, you have to wear a snake around your neck, but that's not the only thing you have to wear. Okay. So I'll move on to a different domain. So here we are dealing with travel time predictions. Now, this is very, very interesting. So you get a lot of traffic data, all of us know, and there are different types of data you can get, LiDAR data, modern ones, GPS is a very standard one and so on. So to cut short the problem that we are looking at, we are interested in predicting bus travel times in Chennai from the GPS data that comes from a bus. And this is a specific route called 19B. which runs from one point to the other. It's a 30-kilometer long stretch. And obviously, there are many trips. And there is historical data of 1,024 trips over a period of 45 days. And we divide that entire distance into 500-meter sections. Okay? Well, that's a choice. You can actually divide it even further. Okay? Whether we want to do it or not. Now, like we were speaking post-dinner yesterday, the traffic in India is a very complex system, right? You have all direct people coming from 360 degrees. Only two directions are left, from the sky and from under the ground. That also is possible, but those are the only two directions. Maybe with the helipads, that can also happen. Suddenly, a helipad can land in front of you. So this taxi, what is it? Heli taxi can land in front of you. We are heading there. We are really missing out on that. So, and then you have the municipal corporation giving you all the challenges that you want to publish in many many good journals. You think that there is no ditch today, there will be a ditch tomorrow, right? And then so on. And then, of course, there are so many other factors. So think of this. You want to build a model that predicts travel time from this historical data over a 30-kilometer stretch. Do you think a single model will work given the variability in space and in time? You have weekdays, weekends, holidays, peak hours, school hours, office hours. Nowadays, actually, there is nothing. Everything is taken up. Morning is all rushing, people going outside. Then school hours, then office hours, and then people going out for lunch, right? Then the school time return, then all the return trip, U-trip. So where is the free time? I don't know in an urban scenario. Anyway, so how do you think a single model will work? You have to really build multiple models. So don't think that you can dump this data into a deep neural net and it'll do the job for you. No. So manually, I have to group the data. Is that also a good idea? Should I go to the calendar and say, today was a public holiday, this was the peak hour, and so on? It's not so attractive. So we asked this question, how do I now build multiple models? Obviously, the first suggestion is take the data, give it to an unsupervised learning algorithm like K-means, right? Because that's the best means that we have right now. It's K-means. And it'll give me clusters and I build models on each cluster. Do you think that's a great idea? It's a good idea, better than a single model. Is it the best? What do you think? Is there some catch there? Well, the catch is that the clustering algorithm has not been told the purpose of clustering. It is saying I'm using some metric that you built in. Somebody who devised K-means told me this is the optimization, this is a cost function that I'll minimize, right? And that's how I'll classify. So you're giving some features. Based on the features, similarity, it'll classify. But that's not the purpose. I want to group data into different baskets for which the model can have a uniform prediction skill in that each basket. How do I tell this to the clustering algorithm? I have two ways. Go and modify the optimization function, right? Or change the features. And that is what we did. So I'm just going to skip that slide. And so this is just telling you what are the variations in the travel times, just to tell you that a single model will not work. So what we did was we used this approach. We said, we will feed the prediction error to the clustering algorithm. So we want the clustering algorithm to take the prediction error and group the data based on that matrix. So all data with similar prediction errors will go and sit in one group. How do I kickstart? And then, of course, put it in a loop. How do I kickstart? I'll tell you, what is the best prediction given a time series? I am asking this question. What is the best prediction? Anyone? Mean. That's a naive prediction, correct? Of course, assuming stationarity and so on. Please do not underestimate that. I'll tell you why. So cricket.com approached us once asking if you can predict the runs of a player. It's a very, in a cricket, cricket is just like madness. I'll even leave my lunch dinner and go play cricket in India. So it's a very fancy thing and it's a very, close to heart game. So they had built a model and they wanted academic help to see if their models are good. Obviously, they were not doing well. So we asked for the data. So they gave us the data. And in cricket, there are different formats, T20, test match, blah, blah, all of those different formats. You know what we found? There's no predictability. So mean is the best prediction. We told them the pre-match prediction, the best prediction is mean. They had built complicated deep neural nets and so on. And they were asking why they are not performing well. Because there's no predictability. You didn't do the test before. Then we told them, once the match begins, then the predictability shoots up. You can start predicting. So the in-match predictions are the ones that you have to rely on. So don't underestimate the mean. So we start this algorithm with the mean travel time, and then we'll put it in a loop. So the results are here. Okay, so that's the idea. The results are here. So I'm showing you 3 different approaches. One, where there is manual grouping, the best I could do. And then I have prediction and clustering done separately. And then the joint prediction clustering algorithm, the JPC algorithm that we call separately. So you can, and what on the x-axis is a trip. So you have many trips in a single day. And the y-axis is the error value. You can see the error bars are shortest for most of the trips with the proposed approach. Naturally, it has to be. And it converges in about 3 or 4 iterations. So you start with a certain number of clusters. It says 4 clusters. You build simple ANN models. You don't have to go for deep neural net models. But when you build those models also, you have to understand that this is a dynamical system. That is one other problem with learning data science from a traditional computer science course. Okay, I don't have anything against computer science folks. Please don't make inferences and quote me wrongly. The thing is, in computer science, by and large, dynamical systems are actually at the periphery, or even close your eyes. So you're shown cats, dogs, peppers, and so depending on the lunch time or petting time, you will show these images, and if your algorithm works on that, you're good. No, that is fine. But come to dynamical systems, Baba, I'll show you what the challenge is, right? So you'll have to really configure the features accordingly. You have to respect the transient nature of the process, feed the transients also as features, okay? That's what we do, and we develop models. So very important to feed transients, the lagged variables. So in the weather and climate world, I find that this approach is totally missing. And now we are trying to, in collaboration with Vishal, and of course, as a part of the Monsoon mission project, we are now trying to come up with this JPC kind of approach for bias correction, right? And I think it will work very well. If the gut feeling is always and very important. So the gut feeling is it should work. If it doesn't work, we'll make it work. Okay. No, but that's the conviction that you should have, right? There are some approaches, but they're just used in a very superficial manner, if I may say. Okay, so moving over to crop yield. We did this in 2016 or 17. So we thought now we are given a different problem from ISRO. So what they wanted us to do is predict crop yields in 2 different states, Madhya Pradesh and Tamil Nadu. 2 different crops. The states are not the ones, the crops are the ones that matter. Don't bring language battle into this. Groundnuts in Tamil Nadu and soybean in Madhya Pradesh. We have data over how many years? 20 years. That's a lot. You think? No, it's just 20 data points. With respect to yield, I have only 20 data points. So heavy data scarcity, right? Now, this is one point that I want to make before I forget. There were people, and there continue to be people who want to live in this end of first principles. I just don't want to go, no statistics, no data. I remember my experience with in one ISRO center where I went, when we talked about time series modeling, the scientists just got up and left, banged the door and left. How dare you actually bring in data? It is corrupting our first principles approach. And so, okay, fine. Then there are these people who blindly believe in data. You don't have to really subscribe to these two. The entire world is in between. So how much of process knowledge, how much of data discovery, database discovery, you want to really marry that very well. When you have lot of data, you can afford to have minimal knowledge. Afford to have, I'm not saying throw away. Which means that when there is data scarcity, the picture has to be completed by a lot of process knowledge. Okay. So you can ask, what is the value of data? Value of data is knowledge, value of knowledge is data. Okay. So you can ask how much is the value of data? And but there is no kg or something like that. I'm not asking that. So the challenge for us was that we had very limited data with respect to yield But we have a lot of temperature, weather data, and so on, satellite images. And then you have some soil moisture data and so on, and then some crop cutting experiment data. So to give you an idea, the other challenge is, look at this. This table gives you some idea of the different sources, the resolutions, and the sampling times. How on earth am I going to actually fuse all of this? So I told my student, let us do the standard, the bull approach, where you take all of this and feed to some Jurassic Park model. What is a Jurassic Park model? A deep neural net with some billions of parameters. And the joke always I like saying is, go to a Tyrannosaurus and give it a sandwich. Like today we are given sandwiches. You give it a sandwich, what will it do for breakfast? It'll keep the sandwich aside and eat you. Right? Because it's not enough for a breakfast. That the same thing happens with these Jurassic Park models. You give very few data points. What will it do? It will fail you when you most need it most. Right? So don't do that. Respect the data scarcity. Consider that. See, like I mentioned earlier, you want to add the chili at the right time. You want to add the salt at an appropriate time. You don't dump all the ingredients in the pan and go to sleep, right? With an automated cooker. You don't do that. So here also we asked, how do we bring this data to in a hierarchical way, in an iterative way? So this is the algorithm that we came up with. We call this as a M-stack model. And there are advantages of this model beside being physically informed. Well, the pins that Dr. Mitra talked about today started with shaping your deep neural net models or ML models to respect the closures. But that is not where it stops. That is only one aspect of pin. There are other aspects of it. So we call this as physics-infused model. So you infuse the physics at different stages. Although we don't call it PAML, it is predominantly an ML model. In a couple of slides, I'll show you how we incorporate the physics, because ISRO said, no, crop simulation models exist. You also have to use that. Okay, Baba, we'll do that. But first, let us develop ML models. So this, what we did, if you look at the structure, the top layer is a pure time series model. Suppose I didn't give you any data, no weather data, soil moisture data, fertilizer, nitrogen, phosphorus, nothing. I only gave you yield data, 20 years. We'll be able to predict. I'll show you what was the result. So this is the first stage. And we used LSTMs, not because it is a popular, we didn't go by its celebrity status. We evaluated ARIMA and so on. And then LSTM proved to be a celebrity here. Again here, the word of caution. So we use the past yield to adjacent districts, right? And also the past couple of years. So those are the features that went into LSTM. This is the red line, is a 45-degree line. Prediction versus observed. Do you like this prediction? It is as worse as the mean. This is for soybean. Now you see for groundnut. Do you like the prediction better than the one for soybean? Just with time series yield, it's different. Why is this different? Explainability. We are trying to still explain crop dynamics, essentially. Right? Again, I said, don't bring language battle, because Hindi is spoken in Madhya Pradesh, Tamil is spoken in Tamil Nadu. No, don't attach to that. Okay. It's just got to do with crop dynamics. But the advantage of working with this, there are two main advantages. One, you know what is the prediction deficit and the value that the external variables are going to bring in, number one. Number two, imagine you lost access to satellite, all the sensors. You need a model to bank on. At least here, there is a model to bank on, right? Then we brought in the external variables in a hierarchical manner. Again, you cannot expect the same model for all districts. So here we have a K-means algorithm here, but variant. In fact, I told my student, Ankana, you go and read the travel time prediction algorithm. It looks very similar. So we are transferring some of the learning from there. And she read the paper and she said, no, I need to make some changes. Go ahead. That's the whole idea. And she came up with this algorithm where iteratively, so we extract one set of features. And for clustering, what do? We only use the fertilizer data because the fertilizers play a critical role. Why is the yield different across districts? Yes, there may be weather conditions, but that is not the primary driver. It's a fertilizer content. It is the nitrogen and phosphorus content that dictate. So some districts have, have higher content, some districts have low. So obviously your model should respect that. Okay, so the ISRO, the SAC people really like that. And here is a resulting model. I will not go further into details. It's already published. I'll give you the reference. And so after going through the final stage, the prediction improves. Okay, and for groundnut also, you see an improvement. So let's just quickly close with physics informed ML model. Doesn't mean that I'm closing my talk. I'll need a few more minutes. Don't be so happy. Typically, I say people clap for two reasons. Either you gave a good talk or you say, okay, thank you very much, you stop the talk. It's up to the speaker to be able to apply a classifier and figure out what. Okay, that's also an ML problem. Anyway, so how do we bring in? This proved to be the most challenging thing because we had no idea of how crop simulation models work. Come on, chemical engineering. I left chemical engineering long ago, except for the degree that I have. And that's it. And even if you're a chemical engineer, you don't understand crop simulation models, right? There are many crop simulation models, but first we have to understand. So it took us 1 year to put the data together. It took us 1 year to understand the simulation models. These simulation models are good for farm level, not for a district level and so on. And they make certain assumptions. They are good at making some predictions, but they cannot take into account satellite data and so on. All the data that goes into an ML model, that's not how the simulation models are configured. So we said, okay, we will use the crop simulation models. It took us time to calibrate these crop simulation models. And there are do's and don'ts for that. I'll not get into that. Okay. So of course, now Ankana is a trained crop simulation model analyst. Okay. So what we said was the change that we will make is only in the first layer. We will choose either an LSTM or the prediction of the crop yield model. The rest of the structure remains the same. Okay. So, the top two ones are showing the predictions of the PI-ML model, physics-infused ML models, to distinguish between physics-informed. For 3 different prediction horizons, by the way, it's not a simple problem. Although Ankara did his MS work, I think she should be given a PhD because 3 temporal resolutions of predictions, 15-day ahead, 1 month ahead, 2 months ahead. And then at the district level, at the tehsil level, and then at the Gram Panchayat level. So really 3 different resolutions. So I'm just showing you for one spatial resolution, 3 different prediction horizons. Obviously, the 15-day predictions will work very well. And here is a comparison between the PI-ML and the without PI. Interestingly, so these are the error metrics. Interestingly, the 15 days ahead PI-ML performs worse than the ML one. You should not be shocked because the crop simulation model has its limitations. Okay. That's because I told you it works at a farm level. Whereas the LSTM has been trained to look at that spatial level. So all this explaining one has to do. Now, the question is, how do I now, what is the food for thought? How do I take these ideas into the climate world, right? We want to come back. The first question is, can we think of a joint prediction clustering approach? I talked about it. So the approach that I just mentioned is called a model error model in traditional data-driven modeling. So you build a model, there is an error, and then you model that error. So we built a time series model, and then we modeled the deficit, right, with the help of external variables. So should we do that? For example, if I'm predicting precipitation, extreme events, forget about everything. Just take extreme events and make a prediction. How far can I go? What is the distance that I can walk? Now predict the deficit. Yes, the physics of the process may not be like that, but having that additive nature to the model gives you explainability. The value that the other, external variables are bringing in, right? The tendencies and everything else are bringing in. So we should really think of this approach as well. And of course, put it in a multi-scale framework. What more? I mean, you can have like 10 papers, right? That's the whole idea. You want to have publications and patents and paisa, the 3 Ps. Okay. Anyway, so there are only 2 things left to be talked about. No, it is true. The academic world has shifted its priorities. It said publication, patents, and money, Hindi word is paisa. Okay, so these three things, if you bring, you are into the system. Otherwise, you are shown the nearest exit door. Okay. Or you are overloaded with something that you don't like. It's typical US academic system that we have adopted. We have borrowed everything. But we have not borrowed the traffic rules, by the way. Anyway, so, so all of this begs, this concept draws our attention to transfer learning. And the last one that I'll conclude is about network models. I'll just quickly talk about transfer learning. So this is a work that we recently did. Just to tell you what is transfer learning, it's very simple. I like giving this example. You learned how to ride a bicycle, and now you want to ride a motorbike. So your brain has understood how to balance. How many days more does it take to learn how to drive a motorbike, right? As against learning to ride a motorbike from scratch. You need more data points, right? You need more learning time. That is exactly what transfer learning does. You learned some other process which looks similar to this, right? And there is some similarity at some scale. Could be temporal scale, spatial scale, phase, whatever scale you talk about. There is some similarity, but there is a difference. You really leverage the model that you have learned and apply it. So here, we apply this to dynamical systems, by the way. A lot of transfer learning that exists is for static systems, but slowly. In fact, we talked about whether transfer learning is applied to weather. See the shocker that I'm going to show you next slide. Okay, this is fresh off the oven type. Okay. So this is an example. This paper was presented recently at an international conference in Japan. It's one was selected as the best paper. What we did was, we are doing temperature control. MISO stands for multi-input, single output, under two different environments. So the typical language that is used is sim to real, source to target, and so on. Source is where you learn, target is what you want to really implement on. So just focus on these three. Don't go worry about these things. So the left bottom here is what the model has learned and how well it has learned on the source. Now I take the same model and apply it on the target, huge bands of uncertainty. And if I have to learn from all over, I need about 3,000 data points again. But if I take this model and implement the transfer learning, which is based on Bayesian principles, and we use Gaussian process regression models, just with 200 points, it has learned and reduced the uncertainty. So whenever there is data scarcity, and whenever you have some experience from historical data, you should use transfer learning. And here is what, at least these are some glimpses, but this is your spot. Seriously, have you traveled in buses in India?
No.
Oh, you should, but do carry a handkerchief with you. You know what the hanky is for, right? To reserve your seat before you get into the bus. You should not go by these Volvo buses. You should really experience the normal state road buses. 100 people getting into 40 seats. Seat scarcity. Put your hanky first. It should not be white in color. It's a regular color. It's some pink, yellow color or something. Put it and you reserve your seat. So you put your hanky here. That's your spot. Again, domain parallels. All right. So this is one of the most recent papers, and we should all read this. I read through this. There was one question, is zero-shot learning. Who asked that yesterday? Oh, the person who asked vanished from today's audience. Okay. Anyway, so when we were talking of transfer learning yesterday, one of the questions was, is it zero-shot learning? So zero-shot learning, again, computer science guys are very good at fancy names. You're trained to distinguish between a cat and a rat. Now you're shown a lion. Can you distinguish? Okay. As against straight away distinguishing between cat and a lion or something like that, the first experience. So you have learned the core principle of discriminating between two species. So the core idea has been understood by the brain that says, yeah, this is also different. Okay. Now, of course, how different it is. And there are, again, different types of transfer learning, transductive, inductive, this, blah, blah, all of that. But the whole idea is going from your existing learning on some system, source system, to a new system, which is similar, but not identical, right? The extent of dissimilarity determines the amount of fresh data that you have to collect. That's the bottom line. Anyway, so I think there's quite a bit that can be done from a reading in this literature, that there are papers where they have trained it on historical simulations because there is data scarcity in the real analysis data, reanalysis data, sorry. So the model learns as much as possible from the simulations, and now this model is ready to be tuned with this few reanalysis data points that I have. Good. So you can actually now use these models to fuse both the simulation and the real data, observed data. Right? So are you ready to transfer your and your model's learning? Is the question that you want to ask. Okay, so last topic, networks. Now, I told you early on that I'll show you a progressive set of complex networks. I should do justice to this screen also. Otherwise, I'll be termed as a leftist, standing there left all the time. Okay. Complex networks, as I told you, is a very new modeling paradigm that has evolved in nonlinear time series analysis. Just to help you understand the development in half a minute, linear time series model, the literature is very good, saturated kind of ARIMA models. I told you SARIMA and so on. But the world is nonlinear. So the challenge with nonlinear systems, I don't have to spell out. When you're dealing, there are so many different types of nonlinearities. The objective is to characterize these nonlinearities in terms of different indices like Lyapunov exponents, Kolmogorov indices, and so on. Yes, people succeeded, but they found that it is still very limited in characterizing these nonlinear processes. Over a period of time, these network models have evolved, and they said the network properties can help me predict, for example, the onset of chaos. Or in biomedical, in healthcare, at least, these are all pilot scale applications, predict the onset of Alzheimer's or any other disease and so on. Of course, it's at a very rudimentary stage, but there is hope. So these networks have evolved in that context, starting with this so-called correlation networks, where there's no directionality, to partial correlation networks. The analogy is total derivative versus partial derivative. Total derivative tells you how one variable changes with respect to the other variable, regardless of what the remaining variables are doing. Partial ones, you freeze the other variables, and then you are looking at the change of variable 1, x with respect to y. So here also the connections are conditioned on the other variables. But still it is correlation network, partial correlation network, or partial coherence network, if you like, if you're a frequency domain guy. Then you bring in directionality, and then you bring in weight. Okay. So we've been working on these networks for the last 17 years. Our journey started from control. From big plants, we wanted to really understand interactions between control loops. And from there, we went to climate and so on. So there are advantages of building networks from data very quickly. You can get strengths of connectivity. That means in neuroscience, by the way, there is this whole literature on causal networks and networks. And there is this notion of effective connectivity versus functional connectivity. Effective connectivity is what you get from data. Functional connectivity is what you know, yes, from data, but without a direction. Then there's structural connectivity, which you know from your understanding of the brain. Effective connectivity is the best because it tells you the reality. And it also takes into account the stochastic effects, and it allows inclusion of partial knowledge. Okay. So when you look at networks, and there's a very nice couple of nice review papers that have come up in the last 4 years, and I've given one such reference here. And there is an internal report that is being written by me for the last several years, and it will continue to be written. Okay, if you want a copy of that, let me know. I don't know when to put a full stop. That's a problem with me. But anyway, so there are so many different types of networks. What distinguishes between them? What is characterized by the node, by the edge, whether it is a directed network, whether it can handle univariate data or multivariable data. And there are so many other factors. So among these, the correlation causal networks are very popular, but in the nonlinear dynamical systems community, the recurrence networks are very popular. It basically captures the states recurring over a period of time, and it captures, it puts those states at the nodes and so on. There is something called visibility graphs also that have a lot of visibility. Okay. So very quick glimpse of, I'll just very briefly talk about causal networks and finally close with the synchrony networks. Just give me 5 minutes. So causality, as was mentioned by Dr. Mitra, is a very philosophical thing. Why does it have to happen to me, especially when I get low grades, when I don't get the salary on time, and so on, right? Those are the questions that come to me. Why? But you have to really, when you apply to data, you have to come up with a mathematical quantification of causality. And there are several attempts that are being made and they continue to be made. But before you do that, you have to understand that there are these temporal forms of causality depending on whether the cause strictly precedes the effect or is instantaneously affecting it. And then whether it is feedback or bidirectional. Then you have variate forms of causality in the variable direction. You're looking at just a pair of variables or you're looking at a pair of variables discounting for the other variables. So those are also important. So this is called pairwise causality versus multivariate causality. So the question is, how do we detect all forms of causality from data? Is it a single method? No, no way. Why? Because the number of definitions of causality is a lot. Okay, in the previous talk, 3 forms of causality were mentioned. The Granger causality, then the interventional one, then there are the SIMS, the counterfactual and so on. But let me tell you, over the period of time, we have also contributed to this this literature. Everybody has to. When you face trouble from the literature, you also contribute to the trouble. Okay, so there are other forms of causality known as cross-mapping, which is very popular in ecology, and probabilistic constraint-based causality, dynamic constraint-based causality, etc., etc., etc. Okay. When you're reading a paper on causal networks, the first question you have to ask is, have the authors defined what form of causality is being detected? If that is not mentioned, please keep the paper for next birth reading. Okay, don't read it. Because that means the authors are not sure what causality they're detecting. It's very, very important to say that. Because every definition of causality has a certain limitation. Granger causality is based, I'll just contrast this Granger and cross-mapping causality because that's the 2 things I'm just going to give you a glimpse of. Granger causality is called the predictive form of causality meant for only stochastic processes. If I am given 2 signals X and Y, if the past of X helps me improve the prediction of Y, then I say X Granger causes Y. But that doesn't capture all forms of causal relationships because a cause can trigger and keep quiet. Right? In many houses we see. And in the Indian Puranas, Narada is known for that. He'll trigger something and keep quiet and the rest of the world will actually fight. And so on. So there are those forms of causality. Then maybe the cause is affecting only the variance of Y and not the amplitude. We don't know. So it's very hard to claim that one form of causality captures everything. The cross-mapping causality, which was introduced in ecology, Granger causality in econometrics, all this eco thing, there is something, okay. It is a flipped form of approach. Granger causality says, I will look at the parent and tell you, whether this is a child. Convergent cross-mapping, the cross-mapping techniques, I look at the child and tell you whether that boy is a parent. Meaning, if I can recover X from Y, and the recovered X has a strong correlation with the observed X, then I'll say X causes Y. Okay. And it was conceived for nonlinear dynamical systems with weak coupling. All these terms and conditions that come with mutual funds in fine print, you have to be wary of. Okay. So the approach is totally different. There are, so this is Granger causality. I just told you, I'm going to skip this slide. And of course, people have extended it. This is a simple case study. I'll just walk you through 3 time series. I'm not going to go through any techniques, but I'm just going to show you these are the 3 time series that are given to me. I have to reconstruct a class of networks, all the way from correlation to weighted causal networks. So here is what we call as a coherence plot, where the variables on the columns are treated as sources, causes, and the rows are effects. Ignore the diagonals. X-axis is frequency. If the coherence is above the red line at any frequency, then that source is affecting that variable. That's it. So you draw the network here. The Z1, Z2, Z3 are the variables, E1, E2, E3 are the inherent uncertainties. Now, this is a partial coherence network which has taken into account the effects of other variables. So, it is discounting for the effect. So, here when I'm looking at 1, 2, 2, 1, I'm not discounting for the effect of the third one. Here I'm discounting. So, it turns out in this application, it's the same. Now, this is called a partial directed coherence. So, you're going from coherence, partial directed coherence. Very nice, terminology development. This is an asymmetric plot, as you can see, because it's a directed measure. Again, the same interpretation, except that I have a shaded plot. Now you can see 2 drives 1 and 1 drives 2. But 3 doesn't drive 1 and 1 drives 3. So you can complete the rest of the picture. This is just a binary problem. All of these are detecting only Granger causality. These are all Granger causal networks. Then obviously we are not happy with this. I have to have my PhD student do something new. So it's not that. There were some shortfalls with this PDC, partial directed coherence. So we come up with this direct pathway function, which not only allows you to build a structure, but also adds a weight to the network. So just to conclude here, this is the true process. This is the identified network. Okay. And the true process here, this is generating model. It is an ARMA process, or rather VARMA process, not the VARMA, VARMA. Okay. Vector autoregressive moving average process. And when we build these networks, we assume a different model. We assume VAR models and so on. So despite the mismatch between the DGP, the data generating process, and the model, still we manage to identify the network fairly good. That doesn't mean it will be valid at all times. Only for large data this works. For small data, the mismatch actually can prove costly. Now, there is another paper for that. Okay, we have done that. Anyway, so there are known limitations of Granger causality. Some 100 things you can list. But there are also commonly misunderstood limitations. Don't get into this trap. Somebody telling you it cannot handle non-linearities. No, that is not true. Granger never said that. Go and read his paper, original paper in '69, and so on. But there are so many other issues with it that you have to be really wary when you read the net. There is enormous literature on causal networks in climate. Everybody trying to say something different and contradictory. One person says, one set of authors say, yes, global warming is because of this CO2 emissions. That is what Granger causality says. Therefore, my paper is great. Then 2 years later, another set of authors say, no, those guys are wrong. Okay, my Granger causality implementation shows this is not correct. So CO2 emissions are not the reason for global warming. Why there is confusion? Because you have not really asked the compatibility of the causality definition and the inference method with your process. Please do that, okay? Not only in causality, but everywhere. So I'll just quickly show you convergent cross mapping and then say Jai Hind. Okay, so just 2 minutes. So convergent cross mapping, I already told you, the idea is you recover X from the manifold of Y. Now don't ask me to now elaborate on manifold. I can, then Vishal will actually not invite again in future anytime. So, or he will dedicate an entire workshop in my name. So X is recovered from Y and from the manifold of Y, and Y is also recovered from the manifold of X and correlated. So for this reconstructing this manifold, you turn to Tarkin's theorem, you construct embeddings and so on. I'll skip this part, refer to the previous 2 weeks ago workshop. So what is the shortcoming of the original CCM? It cannot be really, there's a scalability issue for large gridded data sets. Computationally, there is a challenge. And Sugihara, who proposed this, did not say what is the coupling strength up to which you can apply this method. That's a separate work that we did. I'm not reporting that here. And how do you handle for stochastic processes? There is no talk about it. And multivariable version is required. Yeah, we developed one, but I'm not going to talk about it either. I'm just going to show you how we applied this to a data set from the GCM. And this work came out of a master's tracing, where the whole idea was to computationally accelerate this. And in that process, also make some causal inferences. So these are the details of the data. And we did some basic statistics. So we made some changes to the way the CCM is computed. It's called convergent cross mapping. The reason why it's called convergent is the idea is nice. So you take subset of data, compute the correlation of the cross map. Then you keep increasing the library size, and it has to increase and saturate. If it doesn't, then that means it's all spurious. So that's a nice idea. I really appreciate that. But this increasing library sizes takes away your computational time. So we parallelize it, not parallelize it, parallelize it. And if you don't parallelize it, it becomes parallelized. It stops. So and then we optimize and so on. So there is a broad increase in the computation time. So conclusion on this, we divided into 7 zones based on the uniformity, right, or kind of climatological continuity. And we picked one zone and we built the network. So this is our inference. And when we did that, again, the same story, you have to consider spatial temporal lags. Okay. So for low lags, we found that bidirectional causality exists between precipitation rates. By the way, the variables are precipitation and temperature. Okay. And there's obviously for small lags, the nearby points are connected. For large lags, that is greater lag values, the nearby causalities vanish. And the long ones come up in the northeast direction. Okay, which makes sense climatologically because the one that is far away takes longer time to influence. Okay, so that is what it is. I'll skip the synchronous networks in the interest of time, but if you're interested, we can talk about it later. One thing I wanted to say is when you talk of causality, please make sure you pronounce it properly. A lot of times people say casualty. Including, I'll tell you, when a citation for an award for me was being read out by the then dean, he said, Arun works in casualty networks. That was the casualty of it. That's it. So please don't read it casually. Anyway, so I'll conclude with this modern weather modeling uses hybrid. It says, I will combine the might of numerical weather predictions and ML and see how far we can go. So that is where the trend is. And we are also trying to do that for extreme event predictions. And we are trying to see how we can plug in deep neural nets or any ML model within the NWP or completely replace this NWP, fire this fellow and replace with a deep neural net. So we are deciding whether to hire or fire at the moment. Anyway, hope you're all fired up now. Thank you.
Thank you.
And many apologies for going extreme event, taking more time.
Yeah. No, but I kind of quite enjoyed your talk. Yeah. We have time for maybe
half a question.
As many questions from students, but keep it short.
Yeah. All the curtains are opening, throwing some light.
Yeah.